Okay, hi everyone. My name is Tal, and today I'm going to present Afforest, which is a new parallel algorithm for the computation of connected components in graphs. This is a joint work with the Hebrew University, so a very talented student, Michael Sutton, worked on this, and I'm going to be presenting it now. So, as you all probably know by now, graphs and large-scale graphs, to be exact, they're everywhere. In machine learning, where problems are getting larger and sparser, computational science, where every unstructured grid essentially uses a graph to perform all the computations, and in social networks, where it is used for community and anomaly detection. So essentially, we have these graphs, and we need to start processing them. And the first pre-processing step that is often overlooked is the computation of connected components in the graph. And the reason why we need to compute those connected components is that most of the existing algorithms for graph computations that happen afterwards can just be performed on each component separately. So then this pre-processing step is very important to us. Now, just to be brief about the connected components problem in general, we have a graph, an undirected graph G with n vertices and m edges. You can see one here. What we would like to output for this problem is another array of size n, number of vertices, where each element in the array corresponds to the component ID. So this can be any labeling as long as every vertex residing in the same component will have the same number. So to compute connected components in parallel, there are three predominant algorithms right now. The first one, label propagation, in which each worker can process a different vertex in parallel. And each vertex basically looks at the neighbors of itself and applies a conflict resolution rule, for instance, finding the minimum value, and set itself to the value of the neighbor that, of course, to the value of this resolved conflict. And what happens here is that we propagate the lowest label, and we proceed doing that until the graph converges and the labels don't change anymore. Now, I've taken the liberty to add work and depth analyses for each of those algorithms. So this used the work depth model for concurrent algorithm evaluation. So here, what we see here is the total number of work, total amount of work that we are performing for each graph is the diameter of the graph times the number of edges in the graph, and the depth here is the diameter of the graph because we need to propagate the information throughout the whole graph. And of course, this creates a high level of average parallelism. If we divide the total amount of work by the depth, we get that the average parallelism, which is also a good estimate to how many cores you should allocate to such a problem, is the number of edges, which can be pretty high in large-scale graphs. Second approach is breadth-first search. In BFS, or parallel BFS, we start with any random vertex, and then we use the neighbors to propagate the information. So to push the information along that component using these nice frontiers here, and eventually we achieve a state where we have no more nodes to traverse. In that situation, we will randomize and choose another vertex and continue. So here we see that the work is now, the overall work is reduced. Now it is the essentially optimal number of work. We traverse each node and each edge. But the depth here has and you can also see this in the operation itself. You can see that there is a serialization in the component. So the more components you have, the more sequential operations that you need to perform. And this is also reflected in the depth. A third approach, which is right now, I think, the highest performing in most cases algorithm for computing connected components, is the algorithm presented by Shiloach-Vishkin in 1982. There we construct an auxiliary data structure on the graph, which is a parent pointing tree. So for each node, we start by letting these trees point to themselves. And as we progress with the algorithm, we use the edges of the graph to connect those trees. And I'll show you exactly how in the next few slides. While compressing those trees to depth 1, and eventually we remain with exactly C trees, where C is the number of components, and the number here would be the label. Okay, so where they're pointing is exactly this array that we've talked about in the beginning. So we see here that the average parallelism, the work divided by depth, is the same as the label propagation, but what we also see in this Shiloach-Vishkin algorithm is that it is completely independent of the diameter of the graph. And for that reason, and the fact that it is already the state of the art in computer connecting components, we choose to focus on this algorithm for our paper. So, in more detail, the Shiloach-Vishkin algorithm has two steps, hook and compress, sometimes also called shortcut. In the first step, the hook phase, we loop over all the edges in parallel, okay? And if we have, for instance, an edge here connecting U and V, we look at their parent pointing trees. And then we see here that the parent pointing tree of U, we set it to P1, the parent of V, we set it to P2. If P2 is higher than P1, we just set this high vertex to H and the other one to L. If the high vertex points to itself, which means that it's a root of an existing tree, we connect it to the lower root. And this allows us to essentially hook the trees, and hence the names. And then we just keep connecting those trees according to the edges until we reach the connected components. The second phase, the compression phase, takes all the vertices, okay, each of them essentially creating this tree, right? And we look at the parents of each one of the nodes, okay, so we see here. And if those parents have additional parents, which means that the tree is more than a depth of 1, we simply compress it, okay? So we loop over until we reach the root, and then we directly connect the node to its tree root. And essentially what this leaves us with is that now all the trees are again of depth 1. And what that means is that we can use those trees that we have now discovered to perform additional hook operations. Because as you can see here, it only traverses one step, okay? So we run this algorithm in alternating succession, right? We run hook, then compress, then we get more edges that we can hook, until we do not modify the graph in the hook phase anymore. And this is where the algorithm declares convergence. Now, if we try to analyze the work efficiency of the Shiloach-Vishkin algorithm, let's say that, of course, we have n trees at the start because each vertex points to itself. In the end, we will have C components, so that means we'll have C trees. Overall, if we want to successfully converge with this algorithm, we would have to perform n minus C tree hooks that are successful, that actually modify those trees. Now, in the paper, we define two measures to analyze the convergence of the Shiloach-Vishkin algorithm and also our algorithm. And one of them is linkage. So linkage is very straightforward. What happens here is that the numerator contains n minus the number of trees at iteration t. And the denominator is the n minus c, which is the overall work that we have to do. And what is happening here is that t0, or before we start the algorithm, we have n trees. So this measure begins at 0. And t at infinity, or when we converge, we'll have c trees, so we have n minus c. Essentially, this number goes from 0 to 1 as we converge. The efficiency declared for each iteration is the number of trees that we have now, or the number of trees that we have removed or connected in this iteration, divided by the overall number of edges. Because, as I said, the hook procedure inside the Shiloach-Vishkin algorithm has to loop over all the edges for every iteration. And if we take, for a case study, a real-world graph of a web graph, I think it contains around 1 billion edges or something like that. So it's a standard large-scale graph. We see that the first iteration of Shiloach-Vishkin already performs 99.8% of the actual work towards convergence. And the efficiency is reasonable. Of course, we have to traverse all the edges of the graph. But from that point on, the progress towards complete convergence is very slow. I mean, we're just traversing all the edges over and over again. And there is maybe a better way, right? Maybe we don't need to do all these steps. And this is where our algorithm comes in. So our algorithm, called Afforest, makes 3 key modifications to the Shiloach-Vishkin algorithm. First, we restructure the entire convergence process. So from the hook process, we define a new one called link. The second contribution is we perform subgraph sampling to do that. And I will show again how this is implemented. And the third is, because we perform the algorithm the way we do, we are also able to skip a few edges or not process a few edges in the graph and still achieve the exact solution of the connected components problem. And so first, we begin with this hook link procedure. If we look at the hook procedure in, let's say, higher granularity, we see that this is the existing method. And our existing method changes, so our link procedure changes 2 aspects of this hook method. One, instead of using this PRAM-based concurrent assignment here, we replace it with a compare and swap atomic operator operation. And the second thing that we do is we replace this if condition here, which checks whether the parent of an existing node is actually the root of a tree. We replace it with a while loop that traverses the trees upwards until we reach some kind of a root that is higher than another root, or than another node in the tree. And so just an example to show you how this changes things in the algorithm. Let's take hook, for example, with the edge between 6 and 10, and this is the parent pointing tree structure. And what will happen in this specific case is that we have the node 6 and the node 10. They have their parents, 5 and 9. 9 is, of course, the higher one, but 9 does not point to itself. So the hook procedure will fail, and upon other hooks and compress operations, maybe in a future step it will actually hook those trees. Now, in our link procedure, what would happen is that we will, of course, look at the parents, see that they're not pointing to themselves, and continue traversing this tree pointing, parent pointing trees until we do reach those trees, those tree roots, in which now we see that 4 is actually higher than 1, and that it should be linked to this tree. So what this guarantees, and of course all the proofs are in the paper if you'd like to look at them, is that we do not need to have multiple iterations of link as we do with hook. So every edge, once it goes through this link operation, is already linked, and we just need to call this once. The second thing is that the overall cost that we have, apart from this while loop, is this compare and swap operation, which is, I mean, pretty cheap in current modern architectures, parallel architectures. But the most important aspect, in my opinion, is because every edge is hooked once it's called, we can now process the graph in batches, in subgraph batches. So now we ask ourselves the question, which batches would be useful for us to process? And this is why I said that the second contribution is the subgraph sampling. Now, first of all, if we would run this link procedure on all of the edges, at some point it will become a bit slow, because the link procedure does not compress the trees as the Shiloach-Vishkin algorithm does. So we will end up with very deep trees. So already, any subgraph batch would be better to run with the link procedure, then compress, then run another batch, because it would result in shorter or shallower trees. But now we ask ourselves whether there is a nice or an optimal subgraph batch that we would sample to obtain the convergence at the fastest rate. And we draw intuition from the complementary problem of spanning forests. So a spanning forest essentially is a subset of the edges of the graph. And the number of edges is the number of nodes minus the number of components, because each tree has exactly that number of edges. But that spanning forest, or that subgraph batch, would give us the entire connectivity of the graph that we want to compute the connected components for. And now the question that we ask ourselves is whether we can approximate the spanning forest. And how can we do that? So this is again explained in the paper, but there are ways to approximate the spanning forest. Just sampling a random subgraph with O of n number of edges would be enough. Now, a natural choice for the sampling of these edges would be, for instance, sampling just uniformly, randomly sampling edges in the graph. However, this creates a bias towards vertices with higher degrees. So, for example, if you have a graph and there are two vertices, one vertex has a degree of 128, another vertex has a degree of 1, we would obviously want to sample the vertex with a degree of 1 because it obviously contributes to the connectivity of the graph, right? It is connected to something. However, if we were to randomly, uniformly sample an edge from the graph or two edges from the graph, we would most likely sample two edges from the vertex with the 128 neighbors. So what we do instead is that we sample according to the vertex neighborhood, which means for each vertex we sample a constant number of neighbors. Okay? This means that, for instance, in the case that I told you before, if you have a vertex with a degree 1, we would always include it in this subgraph sample or the batch that we sample. And the second thing that we can do is, because most graphs are in the CSR matrix format, the sparse matrix format, we can directly use the arrays because this information is contiguous in those in the vectors that constitute this CSR matrix format. So we empirically measure different ways to sample the subgraphs. Also in the paper there are more details if you'd like to consult. And what we do here is we compare different ways of sampling the same number of edges. For instance, the first one is to sample different rows in the CSR matrix. Another one is the uniform random edge sampling. Our neighbor-based sampling method, and an oracle method which essentially just returns the spanning forest of the graph. So we again use the linkage convergence, which says how much we have converged from 0 to 1. And what you can see here is that sampling CSR rows is not really efficient. And our neighbor-based sampling method is pretty close to the optimal one. But this is something that we can get without any knowledge of the graph. And the second measure that we look at when we analyze the performance of these sampling methods is coverage. Now, if I were to explain the exact notation here, it would be the number of trees at step t of the maximal component over the size of the maximal component. But essentially, what this means is how much our algorithm at step t has uncovered of the largest component in the graph. Now, it is a well-known fact that most real-world graphs have a giant component and other small components in the fringes. So this number is very important to us to understand how much we have discovered, because this graph is quite large, or this component is quite large related to the rest of the graph. And what we see here is after only sampling 2n edges, we already uncover over 80% of this largest component. So how can we use this to our advantage? This is the third installment of our improvements to the Shiloach-Vishkin algorithm, which we call large component skipping. So once we have performed the processing of the first subgraph batch, we can use this information to, as I said before, skip a few edges without changing the convergence of the graph. Now, how do we do that? Let's say that we sample first subgraph here, and I highlighted all the sampled nodes here in black. We see that we have sampled edges from many of those, from all of those components, but we erroneously determined that there are 3 components in this graph, right? Even though there are 2, because we didn't sample this edge. Now, what we do in order to determine which is the largest component is that we randomly sample nodes from this graph. Okay, we use those nodes to construct a sparse histogram of the component. So for every node, which parent it is pointing to, and then we reduce this sparse histogram to the maximal value, upon which, when we sample another subgraph, we're now going to skip processing these. So let's say we sample another subgraph in green here. All of these edges, which relate to the other components, will be processed normally. However, when we sample here an edge, we sample it, as I said, due to the vertex neighborhood sampling, we sample it attached to some node, right? If this node already points to this largest component, we simply do not process it. We don't even read the edge from memory. Now, this is great for this largest component, but the problem remains with edges like this. That what are we going to do with edges that connect this component to other components, which, again, should be connected? Now, what happens here is, because I said we sample the edge with the vertex, and because this is an undirected graph, the edge actually appears twice. So it will appear once in the context of this largest component, which will be skipped as usual, but it will also be sampled at some point from this node from the other component, which will be sampled and therefore connected. And as we prove in the paper, this also reaches the exact solution of the connected components algorithm. But what we've done here is we have saved a lot of memory reads from those edges, because especially in cases where you have a large component that is very interconnected. So we've already discovered that this component is covered, right? That's the coverage. And we just don't need to traverse those edges. Now, to summarize, the first step of the algorithm links a sampled subgraph, after which we compress those to reduce the tree's depths. Next, we find the largest component that we want to skip. And then we apply another link and compress rounds on the remaining edges while skipping the largest component. Now, as for performance, we measured a wide variety of architectures and graphs. We measured 3 different architectures, so a multi-core Intel CPU without hyper-threading. So these are 2 sockets of 10 cores. An IBM Power 8 CPU with 160 logical cores, but in essence this is a 16-way SMT, and you have 2 cores with 2 processors with 10 cores each. And we measured the Tesla P100 GPU. As for graphs, we reviewed real-world graphs in world maps, social networks, web graphs, large-scale graphs, so like the billions of edges, hundreds of millions of nodes, and also synthetic graphs as Kronecker graphs and uniformly random graphs. And our implementations and the graph specification that we use are in accordance with the gap benchmark suite. And here are the results. So we see here the performance for each of the architectures on each of the different graphs. And the Afforest algorithm is now on the right-hand side. We compare with different implementations of connecting components. So label propagation, BFS, direction optimizing BFS, which in some cases was the state of the art for computing connecting components, not just Shiloach-Vishkin. And as we can see in the results, if we compare just against the Shiloach-Vishkin's original algorithm, we gain pretty nice speedups. So in all graphs, we gain positive speedups, and I've highlighted in bold speedups that are over an order of magnitude. So we can see here up to 67 times speedup. If we compare our approach to the other methods, not including Shiloach-Vishkin, we see that there too we pretty much have high speedups, sometimes even 2 orders of magnitude. However, we have 2 cases here where we have a slowdown compared to the best result. And this is because both of these results pertain to the uniform random graph, which is a very low diameter and 1 component. And such graphs are actually perfect for traversal-based approaches like BFS, especially direction optimizing BFS, which can also process less of that component using this bottom-up traversal approach. But if we summarize the performance, even in the cases where we are outperformed, we're not outperformed by much. This is only 2 point something times difference. And we get pretty good performance pretty much across the board. And this includes CPUs, GPUs, and just to summarize, just to dive into the details, we look at also characteristics of the graphs. So we change the 2 synthetic graphs in different ways. First, we take the Kronecker graph and we vary the average degree. And what we see is, first of all, Afforest is pretty much unaffected by this average degree. And what we see with the other algorithms is, as we change the degree, we also, as we increase the degree, we also change, as we change the degree, we change the diameter, and we can see here that, of course, it affects label propagation because the higher the diameter, the worse it performs. But the direction optimizing BFS can perform actually better because we can still skip those edges. And for the uniformly random graph, we chose a different approach. And what we did over there is that we constructed different versions of the graph where you would have this x-axis presents the fraction of the largest component compared, the fraction of the average component, which means that if this is now 100%, it means that we have one component and that's it. And if we have 10 to the minus 3% here, we have a lot of small components. And as we see here, the performance of Shiloach-Vishkin is unaffected by the number of components, as would be expected. The Afforest algorithm with the component skipping, we reach the same, so we achieve with the 1 component the same problem that we have actually in the main performance results. But as we increase the number of components, we see that, like Shiloach-Vishkin, the Afforest algorithm is pretty much unaffected by the number of components in the graph. However, the direction optimizing BFS increases because of the serialization that I mentioned in the beginning, because it has to process each component separately. And in conclusion, we have Afforest, which is essentially an algorithm that is a best of both worlds, because it can benefit from the Shiloach-Vishkin approach, which is unaffected by the diameter of the graph and introduces a high average parallelism. But also, we can, for instance, skip edges, which is something that traversal-based algorithms can do. In the paper, we also show how this algorithm exhibits higher memory locality than the Shiloach-Vishkin algorithm. And I mean, just to summarize everything, we define a new algorithm, which is now the state of the art in all real-world graphs for the computation of connected components. Thank you for listening.